Hello, today we're continuing our discussion of eigenvectors and eigenvalues. Picking up our discussion from last time, this is material from 5.1. So let me just recall what we're talking about here. Hopefully old news for everyone. Suppose we have A is an n by n matrix. An eigenvector for A is a non-zero vector v such that when I multiply A times v, it's, in some sense the easiest thing that can happen. It's just going to be a multiple of v for some real number lambda, and that's called the eigenvalue. Okay, so that's what we discussed last time, and I want to do some more examples and maybe some bit more of the theory. So we did an example last time where A was, let's see, what was it? It was 1, 5, 6, 2. And we saw that there was we actually computed two eigenvectors here. We took V1, let's say, is 6 minus 5. When you take A times V1, you get 1, 5, 6, 2 times 6 minus 5, which is, let's see, 6 minus 30, which is minus 24, and then 30 minus 10, which is 20. And so this vector is minus 4 of what you gave me, so this implies that V1 has eigenvalue lambda 1 minus 4, right? This is what we talked about last time. And then we also said, let's see, so V2 was the one we actually found by hand last time, and what was it? Let me check my notes here. So this vector was 1, 1. So if you look at A times V2, you get, well, let's do the calculation. You get 7 and 7. So indeed, this is an eigenvector with eigenvalue 7, right? Because when I take A times that vector, it's 7 times what you started with. And so just for a maybe kind of picture here, what this is saying now is if you think about these two vectors, well, 6 minus 5 and 1, 1, let's draw a kind of cartoon picture here. So let's see, V1 is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. So this is the vector V1. And then the vector V2 is 1, 1, right? And so what this is saying is that if you think about these vectors here, and I apply A to either one of them, right, the resulting vector stays in that line determined by them. So for instance, if I take A times V1, right, this thing's going to be, well, it's going to be minus 4 times this vector, so it's going to be kind of off my chart here. But it's going to stay in this line determined by V1. And similarly, if I look at A times V2, well, that's going to be 7, 7. So that one I can actually draw, right? So that's, it's this guy here, A times V2. But again, the point is that it stays in the line determined by V2. So again, these two vectors are in, what I would say behave well with respect to the matrix A, that when I multiply A times either one of them, the resulting vector stays in the line determined by the original vector. And let me just note here that we'll come back to this, that the set V1, V2 is actually a basis for R2. Why is that? Well, right, if I make the matrix of 6 minus 5, 1, 1, this is an invertible matrix. Right, so since this is invertible, one way to see that is take the determinant, but it also, just do a row reduction, you see it has 2 pivots. So what we have here, this is a situation, like I said, we'll come back to. I have a basis for R2 consisting of a basis for R2 consisting of eigenvectors for A. And that's going to be a nice thing to take advantage of once we get there. Okay, so before I say more about that, let me do another example, maybe a little bit bigger. So kind of bigger example now. suppose, let's do a 3 by 3. So, of course, any n by n has possibly eigenvalues and eigenvectors, but let's take this guy here. 4 minus 1, 6. 2, 1, 6. 2 minus 1, 8. And let's say, suppose I tell you that this guy has eigenvalue lambda equals 2. I want you to determine what's called the eigenspace. So don't know if we've defined that yet. So the eigenspace by definition is the null space of A minus lambda I. Okay, so this is what we talked about last time. I'll remind you when we work out this example, but what we saw last time is that we were looking for the solutions of a certain homogeneous system, which, as you know, is, well, the null space of A minus lambda I is, i.e., the solution set of the homogeneous system A minus lambda I x equals 0. Okay. So this is what we talked about last time, that, now I'll do another example and make it a bit more formal. But let's do that. So remember last time that what we saw, so recall from last time, if I wanted to find a vector v such that AV equals 2v, then that's the same as saying that I want to find a vector v where A minus 2iv equals 0. And so here's what I mean by, solving the homogeneous. I want to find the solution set of this system where I have a coefficient matrix equaling 0, right? So a homogeneous system. So here what I want to look at is A minus 2i, which is going to be, well, let me write it out this time, but we'll start skipping steps as we get more used to this. It's this 3 by 3 matrix minus 2i, so 2, 0, 0, 0, 2, 0, 0, 0, 2. All right, that's 2 times the identity. And what is that? Can I fit this here? So this is, basically I'm just taking away 2 on the, not just basically, I am taking away 2 on the diagonals, right? So this is 2 minus 1, 6, 2 minus 1, 6, 2 minus 1, 6. Okay, so that's my coefficient matrix. And now I'm going to solve the system 2 minus 1, 6, 2 minus 1, 6, 2 minus 1, 6. And okay, so it's homogeneous, but I don't need to put this in here, but let's put the zeros. And now let's row reduce this thing. Well, what does this reduce to, right? The 2 rows, second and third rows, are just multiples of the first. So let me scale this by 1/2. This will be minus 1/2, 3, 0, and then a bunch of zeros, right? Those will all clear when I clear below this single pivot here. So what this is saying is I have 2 free variables. So the general solution to the homogeneous, well, it has 3 entries in the vector, right? 2 and 3 are both free. So it turns out when you do your usual vector parametric description, this will be x2 times 1/2, 1, 0 plus x3 times what? Minus 3, 0, 1. Okay? So again, that's the general solution, or the parametric description of the general solution of the homogeneous. What this is saying is that any linear combination of these 2 vectors will be a eigenvector for this matrix A with eigenvalue 2. Okay, so anything you put here, any weight you put for x2 and x3, you'll get a vector that works, that is an eigenvector with eigenvalue 2. Now the eigenspace is this thing, all possible linear combinations. This is called the eigenspace for lambda equals 2. Now remember, a little subtlety here is that an eigenvector has to be a non-zero vector that gives you this, right, A times V equals 2V. So I slightly misspoke, right? So when I say any linear combination will give you an eigenvector, that's not quite right, because you have to take a non-zero. So I should say it's given by any non-zero vector in the eigenspace described here. So I can't take x2 and x3 to both be 0 because that'll give me the 0 vector. But any other weight, choice would give me an eigenvector. Okay, so any non-zero vector in this eigenspace. Note that a basis for the eigenspace, so we talked about bases a couple lectures ago, is given by, the two vectors that are giving me all possible linear combinations. So 1/2, 1, 0, comma, -3, 0, 1. Okay. Okay, so a couple other things I want to mention. So again, this is the main kind of way, let me just to repeat a little bit, if I've given you a matrix A and I told you the eigenvalue, well, the way to get eigenvectors is you first determine this eigenspace, and then, once I have the eigenspace, any non-zero vector in that eigenspace gives you an eigenvector. Okay, so that's, again, just to repeat myself, that's the process for finding eigenvectors given the eigenvalue. So to recap one more time, given an eigenvalue lambda, we can find an associated eigenvector V by solving the system A minus lambda I x equals 0. That will give me the, that's the homogeneous system I want to solve. And the solution set to this, the solution set, so the null space of this guy, null space of A minus lambda I, is called the eigenspace for this particular lambda. And again, any non-zero vector is an eigenvector. Okay, so just to kind of have this recipe in one place here, okay? And later we'll talk about, so next lecture I suppose, we'll talk about how do you actually find those eigenvalues, right? So we still kind of have some work to do because, here I've told you, again, the eigenvalue, and I said, okay, now we can find the eigenvector. Okay, so maybe a couple things I want to just write down. So facts about eigenvectors that I'll maybe let you check the book to verify. But first of all, so maybe fact 1 or theorem, if A is triangular, then the eigenvalues are the entries on the diagonal. E.g., let's say, 3, 6, -8, 0, 0, 6, 0, 0, 2. This is triangular because everything below the diagonal is 0. So this has eigenvalues, the values on the diagonal, so 3, 0, and 2. Another kind of fact that I'll point out here is that a matrix A has eigenvalue 0 if and only if A is singular, right, which means not invertible. Right? So why is that true? Well, oops, so hopefully you could read that. Why is that true? Well, to say that you have an eigenvalue 0 means that you have, this means that you have A times V equals 0 for some V non-zero, right? So you have a non-trivial solution of the homogeneous. That's what saying that you have an eigenvalue of lambda equals 0 means you have a non-trivial solution of the homogeneous, which, as you know, is the same as saying that you have a not invertible matrix. Okay, and the last theorem that I want to write down that we'll prove maybe next time. Suppose we have a collection of eigenvectors, say V1 through Vr, is a collection of eigenvectors with distinct eigenvalues. So each one has a different eigenvalue. Then this collection is linearly independent. So this is going to be a useful fact for what we do in the following lectures. But one more time, you have a collection of vectors that are all eigenvectors and they have different eigenvalues. So remember, every eigenvector comes with an eigenvalue. If they're all distinct numbers, then that set is actually linearly independent. So we'll pick up more on this next time. See you then.